Okay, G6. So, yeah, so this problem makes the observation that if you're looking at a graph of some function, let me draw the graph of a function from R2 to R1. If you want to draw a graph of a function like this, it's going to be some surface, and I'm going to draw something that this is not a, well, let's see here. What can I really draw this well? Yeah, I can kind of sort of draw this. Um, hmm. I'm not going to draw this super well. It's going to be kind of, I claim it's kind of a, sort of a little hill like that. All right. And let's not, I don't want to worry about why that's the picture, but you can go use techniques from chapter 2, etc. I claim it looks kind of like this. So that's what the graph looks like. And note that this graph, specifically, this is the equation, this is the solution to the equation z equals f of xy. That graph happens to look kind of like a little mountain, right? So what we're considering in this problem is that we have an actual mountain whose shape looks exactly like this. And I want to talk about how steep is the side of the mountain at a point on the side of the mountain, now sitting above a certain point in the domain. Now, let's not lose sight of the fact that this shape of the mountain is described by a graph. Points on the graph sit above certain points in the domain. And so down here, this is, I drew a bad picture. This is supposed to be 1, 0. That should have been over here on the x-axis. Sorry about that. Anyway, the point is it's sitting up, the point on the side of the mountain is actually above a point in the domain. And that's just because we're looking at this graph construction, which again is a little bit of a weirdo construction. Does that make sense? Okay. All right, so the problem says, now how steep is the side of the mountain? So if you're standing here, there's you, right? You're standing on the side of the mountain. Steepness means, you know what steep means, right? So how angled is it? So now, yeah, but in which direction? I mean, it's if you move in that direction, it's not steep at all, right? Because that's a lateral. You're just sort of following a contour line there. So generally speaking, when people say how steep is a particular point in the mountain, what they mean is in the uphill direction. So as you're moving uphill. In other words, how steep is it in the direction of fastest increase or in the direction of steepest ascent? So this question, how steep is the side of the mountain, what that's asking is, what is the unit directional derivative in the u direction that is the direction of steepest ascent. So, in other words, this is the direction of the gradient vector. Known fact, the value of the directional derivative in the direction of steepest ascent, this is always the length of the gradient vector. And so what you're going to do in this problem is you're just going to compute the gradient vector for the given function and compute its length. Yeah. Yeah, sure. Does that make sense to everybody? Questions? Okay. Yeah.
What if the question asks for the rate of change?
Rate of change? Well, that wouldn't be a very well-phrased question because the rate of change of the function depends on which direction are you moving. And nowhere in the problem here did it actually say, by the way, you're going to be moving in a particular direction. So steepness just says, like if you were to fall and start rolling, how steep is it in the direction that you're going to be rolling, right? In other words, just I guess it's a kind of a maybe it's a linguistic idiom perhaps that steepness without a direction indicated means steepness in the direction of fastest increase. But when you say what's the rate of change, Well, now we could be talking about the rate of change in a variety of different directions. I mean, the rate of change of the function as you go in that direction, well, that's one thing, but it's totally different as you go in that direction.
Say the rate of change on that unit sector.
I'm sorry?
Say if it asks for the rate of change on that direction.
Yeah, if the problem asks for the rate of change as you move in this direction, in that direction of fastest increase, then yeah, that's length of the gradient vector. Yeah. Yep. Okay, let me stop the recording.